GATE 2019 Metallurgical Engineering Question 42. A 50 mm sphere of solid nickel is oxidized in a gas mixture containing 60% argon and 40% oxygen by volume. The rate of oxidation of nickel is controlled by a rate of transport of oxygen through the concentration boundary layer. The rate of oxidation in moles of nickel per minute is, now the given data is, the total pressure is 1 atmospheric pressure, the temperature is 1173 Kelvin, the concentration of oxygen at the surface of solid is assumed to be 0, the boundary layer mass transfer coefficient is given to be 0.03 meter per second. The value of universal gas constant can be taken as 8.205 into 10 raised to the power minus 5 meter cube atmospheric per Kelvin per mole. We can assume ideal gas behavior. With this given data, we will assume linear oxidation rate, where the linear rate law can be expressed as W is equal to K into T, where W is average weight gain per unit area, T is the oxidation duration, and K represents linear rate constant. Now in this problem, the oxidation rate is controlled by the rate of transport of oxygen through the gas phase to the gas scale interface. Okay? And in these conditions, the rate constant is represented as the molar mass of molecular oxygen into the mass transfer coefficient into the concentration difference of the oxygen, where M represents molar mass of the molecular oxygen, which is around 32, K is the average mass transfer coefficient, and C with superscript of G represents molar concentration of oxygen in the bulk of gas phase, while C with the superscript of asterisk represent the molar concentration of oxygen at the gas scale interface. Okay, so we will use this relation in solving this problem. Now first of all, let us find the value of the molar concentration of oxygen in the bulk of the gas phase. Okay, since it is given that we can assume the ideal gas behavior. So the ideal gas equation is PV is equal to nRT, okay, where now N by V is nothing but the molar concentration. What is molar concentration? It is the amount of substance of solute per unit volume of the solution. Okay, so that's what we need to find in the bulk of the gas. So N by V is nothing but P by RT. P represents the partial pressure of oxygen. Now what is the total pressure? It is 1 atmosphere and 40% oxygen is there. So partial pressure of oxygen is going to be 0.4 atmosphere. The value of R is given to be 8.205 into 10 raised to the power minus 5. Units are meter cube, atmosphere, Kelvin, mole, into temperature. Temperature is 1173 Kelvin. Upon solving this, we will get 4.156 mole per meter cube. This is the value of molar concentration of oxygen in the bulk of gas phase, mole per, this is cube. Now putting the value of molar concentration of oxygen in bulk gas phase in our equation A, we will get the value of K as the molar mass of molecular oxygen is 32 gram per mole. The value of K is given to be 0.03 meter per second into the concentration difference. It will be 4.156 minus, since the molar concentration of oxygen at gas scale interface is given to be 0, so we will use this value 0. The unit will be mole per meter cube. Fine. So it will be equal to 3.989 gram per meter square per second. But since we are interested in moles, so we have to divide it by 32 to convert it into moles. So K, value of K in mole per meter square second will be 3.989 divided by 32. That will give us 0.124 mole per meter square per second. So it is per meter square. So since the geometry is spherical, so we will use the relation. The surface area of a sphere is 4 pi r square. The radius is 25 mm. 0.1244. So unit will be moles of oxygen per second. So upon solving this, we will get the value as 978.7 mole of oxygen per second. Now since we are interested in minutes, moles of oxygen per minute will be, comes out to be 58,722 mole of oxygen per minute. Okay. Now how does the oxidation of nickel takes place? It is like this, nickel oxide. So in this equation you will observe that the number of moles of nickel are 2 times the number of moles of oxygen molecule. Okay. So K for moles of nickel per minute will be 2 times the K for mole of oxygen per minute. Okay. So it will be 2 times 58,722. It will be equal to, there is one correction is needed. I missed 10 raised to power minus 6 here, because, and here also 10 raised to power minus 6 and 10 raised to power minus 6. Yes, now it is correct. So it will be equal to 7444 into 10 raised to power minus 6 moles of nickel per minute, or it will be 0.12 mole of nickel per minute. Okay. To know more about this concept, kindly refer lecture 11, VLSI designed by Dr. Nandita Dasgupta, Department of Electrical Engineering, IIT Madras. Thank you.